and welcome back. Today we have 606 construct string from binary tree. It says here that given the root of a binary tree, construct a string consisting of parentheses and integers from a binary tree with the pre-order traversal way and return it. Omit all the empty parentheses pairs that do not affect the one-to-one mapping relationship between the string and the original binary tree. So the main idea is we are given a binary tree. A binary tree has where each node has at most 2 children, and we are to return a string from which we could reasonably reconstruct that tree. But we can omit the ones that do not affect the outcome. And if we go for an example here, let's say we have, first of all, pre-order. So pre is, we always start from the self, and if it's pre, then we care about self, and then only the left, and then right. So we put ourselves before the children. So us first, and then the children. If it was post, this would be reversed, where we do the children first. So our left and right children, okay? And then only, so our children first, and then us. That's post, so we're putting ourselves after the fact, whereas here we're putting ourselves before the fact, and in order would just be, going in order. So left, and then let's say we're in the middle, so us in the middle, and then right, in order, okay? But here we're actually working with pre-order, so let's put that back, pre-order. So much cleaner. Pre-order is self and then only our children. Okay. So let's say we have a node out here. To reconstruct this tree, and the format is self and within parentheses left, within parentheses right. Okay, to reconstruct this tree, we can say 1, and then left is nothing. There's nothing here, nothing here. So both our left and our right are empty. However, do we really need these two to reconstruct this guy? Could we reconstruct it with just this? Indeed, we can. So this suffices. Now, let's say it's not just the one node. We have a full tree. A full tree is the best example of this, where we have the self, and then the left, and then the right. With this, we could reconstruct this. But what would happen if instead our right side is no more? Then this becomes empty and we could get away with just this. However, what happens if our left is empty and our right does exist? So our right is no longer empty, our left is empty. Could we potentially get away with 1 and the original is 1, left is empty, and then 3? Could we get away with this? We cannot, because the left side is positional. So it's the self, left, and right. If there is no right, as in this case, we can assume that the right isn't empty. However, if the right is not empty, but there is nothing on the right side, there's only something on the left side, then we will confuse 3 to be on the left, and we would reconstruct this guy as 1, 3, with nothing here. Another way to think about this is, let's say we have some integer value 2. 2 is equivalent to 2.0, and that's equivalent to 2.0.0. These are all equivalents. Okay. 2.1 is also equivalent to 2.1.0, and that's also equivalent to 2.1.0.0. endlessly. However, 2.01. Now, we have an empty value, and then we have a 1. So this is not equivalent with 2.1. We need this value for context. This and this are not equivalent. We need that. Maybe, yeah, hope that makes some sense. Or hope that was relevant. All right, so can we construct the code version of this? Of course. What did we do with our drawing? We started with ourselves. We always start with ourselves, and then whatever's processed from the left is added within parentheses, and whatever is processed from the right is added in parentheses. However, one thing is if there is a right, or if there's a right, no matter what, we add the left. If there is a left, of course we add it because there's a value. But even if this were null and right had a value, we would add it because we need the context. Whereas if left were not null, but right was null, we can omit the right. Just like if both were null, we can omit both. Okay, so for DFS, we're taking in some node, and the base condition standard is if not node, then we're done, just return an empty string. However, let's initialize our build string with the string value of whatever our current node's value is. Let's process our left and right children. Left is going to be DFS of node.left. Right is going to be DFS of node.right. We process them. And we have our build string, which is just our current node's value. Now, only if if there is either a left or a right. If there's a left, we anyways need to add it because there's some value. Even if it didn't have a value, if we have a right, we must still add the left for context. And then we add to our build string. Remember, the value goes inside parentheses. Inside parentheses, we interpolate our left value, and then for the right, if there's no right, no worries, we ignore. Remember, if there's no left or right, we don't add left either, which means this won't get processed either because there's no right. But let's say there is a right, then we add to our build string our right, and at the end, we return our build string. Okay, so we take in some node, we initialize it with our current value, we pre-process the left and right string values, and only if there's either a left or a right, then we add the left. If there is a right, we add the right. If there's none, we don't care. If there's no left nor any right, then we add nothing, and we return the build string. Build string default has the current node's value. We can initialize this with, or call this with our root, and since this is returning the build, we can return that directly and submit. And there you have it. We have 606 construct string from binary tree. Thanks so much. Happy coding. See you next time.